Professor Chintan, I see your kappa. Yes. Very,
Very important.
very important. Yes. So, how was your hiking?
Oh, yeah, it was in Scotland. It was
So,
very eventful, at the same time a little boring. So that's good.
okay. You didn't see the Loch Ness?
That's what I mean by boring. So it's good that we didn't see the Loch Ness monster, but other than that, it was very eventful.
Oh, nice, nice, nice. Anyway, I'm sure you didn't expect to see one, but you're hoping maybe against hope. Good, good, good. So we are almost set, a minute left. So when does your university reopen?
Amsterdam University, like we open in September for students. So yeah, so that's when the real teaching starts. I would start teaching in the second quarter, so that's mid-November. So I still have a little longer vacation
Nice.
away from teaching, but okay, there's never a vacation for us.
So, Floris, you don't have such things. You keep doing your research. Am I right?
Yeah. When was the last time I went out of Japan? Just for a conference in London a few months ago.
Oh, so you are on the grind all the time.
Yeah.
So, yes, I think we have reached the right time. I think we should maybe start off, if that is okay.
Yeah, let's go.
Yeah, okay. So ladies and gentlemen, good evening to those of you who are from India and Japan, and very good morning to those who have joined us from the other parts of the world, US and Europe. I am Saideep Ratnam. I am the Chief Operating Officer at MIJSC at IIMB. Mizuho India-Japan Study Center is a center of excellence at Indian Institute of Management, Bangalore. And we are delighted to welcome all of you to MIJSC's 5th webinar on our panel discussion series, which is titled Meijin Samba. It's also known as Expert Conversation. And in the overall scheme, this is the 23rd webinar in the webinar series. We started this right at the peak of the coronavirus pandemic in August of 2020. This webinar actually aims to foster a discussion on a specific topic amongst the various group of esteemed panelists, both from India and from Japan. And we will share their diverse perspectives, sometimes maybe synchronized perspectives. We will see how this discussion goes with a large audience. Our panelists who are experts in their respective fields will provide valuable insights. And what these insights will have high quality information in the areas of various areas of management, technology, and of course, society and culture. Before going into the discussion itself, let me give you a brief introduction, something about our center as well as about the topic that we have today. As I mentioned, it's a center of excellence at IIM and was set up basically as to increase the collaborative initiatives amongst the academia, industry, policy agencies, as well as the society at large. The focus of this center is to strengthen India and Japan bonds by promoting or focusing on academia, industry, and societal linkages. Today, we are very honored to have two very distinguished panelists with us. Professor Chintan Amrit is an associate professor at the Department of Business Analytics, University of Amsterdam. He did his master's at Indian Institute of Science in Bangalore, India, and did his PhD in coordination in software development from Netherlands, University of Twente. His research interests include business intelligence through machine learning, then open source development, mining of software repositories, and he has applied all the analytical tools or analytics aligned with UN's Sustainable Development Goals. Professor Amrit has an extensive publication record, I think over 70 research articles to his name. And he serves as a department editor at IEEE, Transactions in Engineering Management. He also he's a coordinating editor for Information System Frontier Journal. And he's an associate editor at Piaget Computer Science Journal. He's an active participant in academic community, and he regularly chairs tracks at the European Conference on Information Systems and many other such conferences the world over. So thank you for accepting to be a part of this webinar today, Dr. Chintan.
Thank you for inviting me. Real pleasure to be here.
Thank you. The next panelist is Dr. Flores Eric. He's a permanent researcher at the National Institute of Advanced Industrial Science and Technology. I think it is AIST for short. This is located in Japan. His work centers around bridging the gap between the virtual and physical worlds. And he develops tools and techniques to model real-world conditions for verifying the correct behavior of robotic systems. Flores has contributed to various projects sponsored by organizations like the New Energy and Industrial Technology Development Organization, as well as Japan Science and Technology Agency. He has earned his PhD in human informatics and from the University of Tsukaba. And his research focus, starting from his PhD thesis, was on reactive programming using procedural parameters for end user development and operations of robot behavior control. So very interesting background. And now he is fully into a research type of environment. So as I was discussing before this, he doesn't have any teaching load, I presume. So he can focus full time on research. So thank you again, Dr. Flores, for agreeing to be a part of this panel discussion today. Thank you.
Thank you so much. It's an honor to be here.
Thank you. The panel presentation for today, very highly anticipated webinar, is titled, Don't We Have ChatGPT? Problems and Challenges in Machine Learning and Robotics. So data-driven machine learning models have become pivotal in addressing real-world challenges within corporate businesses. Nevertheless, a prevalent hurdle arises, and these models are often using or having the limitations with reference to the data, both in terms of quality and, of course, some quantitative challenges as well. But quality becomes an issue, including issues of sample size, includes challenges of scarcity, noise, and other challenges like being incomplete in terms of coverage, whether it's fully covering the aspect that we are exploring. This presents a significant barrier for developing or striving to develop accurate, predictive machine learning models. Of course, ChatGPT is one, but we are going to generalize this topic, not focusing on ChatGPT, but on these predictive AI predictive models. And what are those challenges? Because this is the way the world is going to go. And we need to understand today, hopefully by the end of this panel discussion, we will be getting a good idea about the nuances and nuanced distinctions between practical machine learning or ML models and their deep neural network counterparts. And the crux of this disparity lies in the differing scales of data availability, while practical scenarios entail small, sparse, and noisy data sets. So this is the challenge I think these two experts in their fields will be addressing today. The central theme of the dialogue will revolve around comprehensively exploring the multifaceted landscape of data-related challenges. And the panelists will unravel the inherent problems and perils that arise when dealing with such data issues. Additionally, they will shed light, hopefully, on potential strategies to effectively overcome these challenges within the context of machine learning and creating models from that. And domain adaptation will be the center stage for this discussion today. This strategic approach involves learning from one domain and applying these insights to another. Something like, distinct domains which are different from each other. The potential of this technique, and this is a very powerful way to do it and learn quickly, but the potential to do this lies in its ability to address data-related obstacles and facilitates cross-domain learnings and adaptation. And we hope that in this presentation, as well as the discussion that will follow, the conversation will shift from machine learning aspects to its cousin, which is application on robotics. And here, hopefully, Professor Dr. Flores will focus on the application of something he calls it as generative adversarial networks. So adversarial networks, or GAN to be short, in short. So both he and Professor Chintan will elucidate how these GANs or GANs can ingeniously create relevant data, thereby enhancing the effectiveness of these models, even when faced with limited or insufficient data sets. So this discussion promises to offer valuable insights into the challenges posed by data limitations in machine learning, innovative strategies for mitigating these challenges, and the potential impact of GANs in the context of robotics, as well as in predictive modeling. The structure for this discussion would be a 15 minutes context setting by each speaker, followed by about 35 to 40 minutes of discussion with me as the moderator. And finally, we will open it for discussion with the audience. So you as audience, if you can jot down your questions as and when they occur to you during the presentations, and put it on the chat box. Then we will address them once the discussions are over. So we eagerly await this thought-provoking contribution for today's webinar. So may I ask Professor Chintan to start with the presentation. Thank you.
Thank you very much for the wonderful introduction. From about me and about the whole topic in general. In fact, you did such a great job. I was thinking there's no need for the presentation. Nevertheless, I'll go ahead and share my presentation that I've made.
Are you pulling my leg?
I'm sorry?
Are you pulling my leg, I said?
No. I was really honest about it. It was a great time for summarizing everything that we had planned to present today. So much of this work, I have to say, is some of it is like under review and yet to be published. So many working papers, and much of this work has been done with under collaboration with PhD students and other researchers in different universities. So I'll be mentioning that as we go through the slides. But before I start, I have to make a disclaimer. This talk is not about ChatGPT, so we put that in the title to attract more people to this webinar. I hope you're not disappointed. Rather, the talk is about understanding, let's say, the challenges, as Professor or Mr. Ratnam said, problems and challenges in practical machine learning problems. So these are problems that are actually faced by different companies and institutions, educational and commercial, for solving their own business problems. So that is what we are focusing on, at least in my part of the talk. And Dr. Eric will talk about things about robotics, so something similar. So before I go ahead, I thought I will just give a very brief introduction on what machine learning is about, except for the part that Dr. Eric will talk about later. So that is more like reinforcement learning, and that's much to do with robotics, but I will be looking into, let's say, standard machine learning, or little more standard machine learning. So on the left side here is what we call a supervised learning. And this basically deals with labeled data. So you already know, okay, which part of data. So you're dealing with trying to predict whether a shape is a square, a hexagon, or a triangle. Much of them are labeled, right? So assuming that this is a complex task, let's go with that. But it could be anything, like you're trying to predict if a particular patient has cancer, for example, or if a criminal is really a criminal based on data about the person in a particular case. So let's see this. So here we are trying to make it pretty simple, and we are trying to predict the shape of this object. And we have labels in the green below. We have hexagon, triangle, square. And what we basically do is we train a particular machine learning model by feeding it, the data. So we say, okay, so these are the labels. Try to learn that, okay, 6 sides basically is hexagon, and try to learn that 3 sides is a triangle, and 4 sides is a square. And then we give it non-labeled data, like what we call test data, and then see how well it has learned. So if it's able to predict that correctly, that 4 sides like this, right angles and all that is a square, and 3 sides, perhaps not equilateral triangle, but something else is a triangle, then we're doing well, right? So then we have actually learned something from the data, and the supervised learning algorithm really works. On the other hand, we have something called unsupervised learning, which kind of is, let's say, deals with little more complex data, which is not easy to perhaps even label. But in this case, okay, for humans, it's easy to label, but it's slightly more complex in the sense that there can be more features or more aspects of the data that might be very hard for humans to even explain, right? So if you have all the features, then and they are very small and simple, then yeah, you have supervised learning. But also sometimes you need the computer or the algorithm to learn by itself by seeing the data, and then understand the patterns by itself, and then try to predict, okay, what kind of object it is. So there is this thing called unsupervised learning, and where you give it unlabeled data. So we don't know, okay, which is a cat, which is a dog, and it tries to understand the way the pixels of the dog is arranged, that it's really different from a cat. And then finally you can say, oh, this is the output, this is a bunch of cats, this is a bunch of dogs, because the pixels are arranged in a different way, more like a dog and more like a cat. I'm simplifying it for the sake of this one simplified slide, which is, I think, I don't know, a 10,000 meter view of a kilometer view of the area, but of the domain of machine learning. But okay, this kind of gives you an idea of what might give you a better idea if you didn't have it before, of what we're trying to do with supervised and unsupervised learning. So very quickly, I will now go into what we are doing in this area. So these 2 pictures have taken from Java Key Point, a website. Okay, it's not generated by me. But from now on, I'll be giving the citations of all the things I take from. So as Mr. Ratnam said, the focus of this talk is more towards why domain is such a crucial thing in data analysis. So this is a nice kind of figure, I think, generated by a PhD student of mine who graduated in 2016. And basically, the diagram says that the world consists of many systems and many domains. Okay, so what we see in our data is a filtered version of that world. And sometimes the data that you see for a particular problem can contain important aspects of that you can actually work with. And sometimes this filter that you see through your data itself might not contain those important aspects that are so essential in making a good model, a supervised or unsupervised model, like in the previous, like I showed you in the previous slide. So let me explain a little more about what we mean by domain. So we have something called domain intelligence, this slide, this picture on the right. Domain intelligence basically is a concept coming from this professor in Australia, Long Bing Kao, and it basically includes 2 important aspects of the data. Like you're looking at some data, it has some domain knowledge and it has some prior knowledge. The domain knowledge gives you some insight into what exactly is happening in that particular case. So as I will show you in a few examples in the next few slides, that some cases, it's very important to understand why certain things are happening the way it's happening. So you have, for example, a case where you're trying to predict the arrival time of trucks in a distribution center. It is really important to know why those trucks are being delayed, or how the driver thinks, how they work. This is the inherent knowledge behind that particular case that is encapsulated in this term called domain knowledge. So this contains all those case-related aspects that are important for that particular case. Whereas prior knowledge is like, let's say, the mathematical knowledge behind applying the machine learning model to that particular domain, right? So it can be things like, we know that, okay, for this problem, this is the best algorithm that works. So that kind of knowledge that is purely, let's say, algorithmic or mathematical, that is called prior background knowledge. So there's a distinction between these two concepts, the domain knowledge and the prior background knowledge. And this distinction was also very well brought about in this paper that we saw from Van Groot. And I'm afraid I don't have those citations here in this slide, but okay, if you send me an email later on, I can share them with you. But they are also in, they are also in this working paper that, is not yet published, but is under review or under preparation for submission. So much of this concepts that I'm trying to explain today are like working papers. So they are not like exactly peer reviewed. So there is some potential for improvement in many of these concepts. So let's start with some examples of data. So here I have given you some concepts, and these are all at a very high level. So in order to make them more clear, I have some examples from actual cases where hopefully I will make some of these concepts that I just explained more practical and more clear. So one of the places where we applied these concepts is AIS Data, where we try to understand what is going on with the data itself. So AIS is this data that all ships and barges and boats, I think, which want to go into any harbor needs to have and deal with. So it's just like a transponder put on the ship, which basically suggests its location, its current location. And like a GPS transponder, they could have used the mobile phone, but they wanted a particular way in which they know that it's really a ship they are talking to and not somebody walking around the street. So they have specific transponders for that. So the devices, which I don't think are very expensive. This is called a AIS kind of a transponder. And I might be not using the exact technical term, but bear with me. And then you need a way to actually catch that data. So we have servers, and you can build your own server using a simple antenna. And the idea is that these antennas actually figure out, okay, we can gather the current location of the ship or barge or whatever boat, and speed of the boat, and direction of travel, and size of the boat. You can get a lot of such data with the AIS, but it's quite noisy. So at some point when we are dealing with AIS data, we saw that the ship is inland on the highway. So that's naturally not possible. So we see that there's a lot of noise when even it comes to the GPS data that this ship actually gives. So in this paper, we looked into all the possible perils that you can face while dealing with such data. So that's the paper below. And here in this right side of this picture, or right picture, you can see that we actually try to list all the perils. So this is something like a mind map. So we have tried to add all the perils into this mind map to make it more understandable. But maybe there is more nuance than just what this picture actually captures. So we see that peril number one is all this around it adds noise, right? So that's a very simplified way of saying that equipment quality, that is the equipment that the boat might have, and the receiver also, the server has, all this adds to the noise in the data, right? So external conditions, human input, because a lot of AIS data is also inputted by humans. There's also the data source that adds noise. And much of this noise adding actually leads to incomplete tracks of the boat. So not all the complete track is can be seen. and sometimes it leads to too much information, which is like information overload for the person trying to understand this AIS data, right? So from the port, for example. And also leads to a lot of dense, okay, we also have a pedal that is dense traffic and so on. So, but of course, there are also promises from the data. So it's very nice that such AIS data exists, and it prevents, actually it can be used to prevent vessels from colliding and even predicting what time a vessel is expected at a terminal, sorry, a harbor. So that is like an idea of data and what we are trying to look at, what I'm trying to look at in this in our research. But I want to distinguish between this kind of data, which is kind of sensor data, which is kind of streaming, and there can be a lot of it, right? So even though this data is noisy and has all these perils, there can be a lot of this data. And given that size of data, which is very important, it can kind of compensate the noise. So there was a paper long ago, I think by Yahoo researchers, which said something like the incredible effectiveness of big data, right? So if you have large amount of data, eventually you can get interesting patterns from it and you can do something with it. That's the amazing thing about big data. But many of the problems that we are seeing in industry and actual practical problems, they don't have this kind of big data. So just giving you an example, we won't go into it in much detail. When we have such data, we can use something like a deep learning. So basically, deep learning is these where you have many layers in a neural network, and each layer does something with the data. In this case, we are pre-processing the data at one layer, and then we are feeding it to another layer, which is trying to understand the patterns visually in the data. That's why we use something called convolutional neural network. And then there is this new concept about attention. I think many of you might be aware of it. And many of the LLMs also use attention. So this is and so we also use that here. And then there's dropout. That basically means that some of the nodes in the neural net, it's not a fully connected neural net. And okay, some of the nodes are not really used. So we drop out the links. And then we concatenate the data at some point. And then we use what is known as a LSTM, which is a kind of a RNN, recurrent neural network, which is basically a way to even remember older data. And because this data is sequential, so the AIS data, right? So the GPS data over a period of time is also kind of sequential. So that's why we use the concept of, that's why we use LSTM to remember the previous location of the ship so that we can easily predict the next location. We concatenate all this, use a standard feed forward, and then we, with all these layers, we can predict the arrival time. Again, this is, I won't go into much detail in this, but this is possible when the data is large. But what we see in many of our practical projects is that the data is not large. So data is small, and this is where the real problems come when the data is smaller. So here we did a project with a World Food Program, and in the Sahel region of Africa, we tried to figure out how much, what is the extent of malnutrition faced by children below 5 years. I might be a bit wrong there. I think it's around 6 months. So basically what we do is we look at the burden of wasting, what is called wasting. And wasting is basically this medical condition where the width or the diameter of the arm of the upper arm is taken, and to determine if there is when the child is actually eating food, whether the food is actually absorbed by the body or is going through without being absorbed. So this is a condition called wasting, and the idea was to identify the burden, the extent of child acute malnutrition in the Sahel region of Africa. So Sahel region, as I will show you in this figure, is made up of all these countries which actually have a lot of food insecurity. because the Sahara Desert is on top, they get all these hot winds and nothing much grows in this place. They have incredible amount of food insecurity, and because of that, World Food Program needs to actually deliver food to many of these countries over a period of time. But also they have a lot of wars and other situations that actually increase this food insecurity, leading to acute child malnutrition. So what we have seen is this is actually over a period of time. This is 2019. And some of this could be also because of the data was not available. And some of it is also because of COVID, that we have seen that the amount of acute malnutrition has actually risen, has increased from 2019 to 2021. This is where we had the last data set from. So if I'm, so 2019 to 2022, I think. So so there we have 19, 20, 21, sorry, 3 years. And as we see here, so I think this is 19, this is 20, and this is 21. It has increased. And the more dark these countries are, that's the higher the amount of the extent of burden of child malnutrition is, right? For that particular country. So these are the countries, and this is the kind of hotspot data. And what we did with this is we tried to predict the possibility of actually figuring out or predicting the extent of child malnutrition, given the data of 1 year, can we do it for the next year? So given 2019, 2020 data, can we actually predict for 2021, and then check with 2021 data how well we did, or how well our algorithms did. The use of this is that potentially World Food Program could use this in future to actually divert its supply chains to send it to the countries where there is higher child malnutrition compared to the other countries, right? So the hotspots, send it to the hotspots. So that is the idea. And or it's actually it's slightly different from food itself. So they have to, it's kind of a medical condition, so they need to maybe send more doctors or to that region, right, to handle this particular thing. So so what we did here was we came up with two ways in which we can handle the data. We have used supervised methods, like I showed you in the first slide, and unsupervised methods. And then we hope that we arrived at a decision support system. And again, this is under preparation to submit to a journal. So this is not peer reviewed yet, not entirely. And what we saw here was that, like I said, small data. So we had very little data for each of the years. And how do you deal with it, right? So when we even saw the ground truth in the data. So the ground truth is basically the burden data that I'm talking about. So the extent of the number of children with child wasting, acute child malnutrition. We see that the ground truth itself could be noisy. So in this case, that means the burden information that we get from them through many means, they use surveys to collect this information, that itself could have some noise. So now what do we do with it? So that is the question. So how do we figure out it has noise? When we actually predict it, we get very low, even different methods, we use different machine learning methods, we get very low direct accuracy. And if we use one-way accuracy, so we don't exactly predict the high, medium, low. So we have 3 levels. We don't exactly predict the right level, but we are okay with predicting a level 1 away from that level. So we don't mind if it's low and medium read together, then our accuracies go higher, right? So maybe so that brought us into thinking into maybe, because much of the data doesn't seem very noisy by analyzing it, maybe the ground truth itself was noisy. So what we got, the actual child malnutrition data, the target variable, so to say, that is the ground truth. Now, suppose we generate the ground truth by ourselves. So what we did here was we use unsupervised clustering. It's a simple k-means clustering, which is a way in which we cluster data based on how far the data is from each other. So the distance kind of metric. So if the data is very close to each other, they belong to one cluster, right? So pretty much the English understanding of clustering. So when we cluster the data based on the way the distance of the data points to each other, and then use this generated ground truth, we see that our accuracies go up. Of course, you might be thinking, hey, this is kind of cheating because, okay, you use your same data to generate the dependent variable, and then you're using the same data to predict that particular independent or the dependent variable that you just created. But we, of course, manage this by using different parts of the data, right? One part was to generating and another part for testing. So that way we go around that problem of circularity in logic. So, so that is what we've done, and then we see that okay, the results improve because the ground truth itself could be noisy in this case. So that's one way maybe in which you can deal with noisy ground truth data, or where the target variable itself is noisy. I'll go into something else. So this is a slightly different domain, like different area, going from medical child health to supply chain. Here we were trying to predict the arrival time of trucks and ships. So this on the right is barges and ships, like I showed you earlier with the AIS data. But here we were dealing with not very large amounts of data, because when we have to get data from actual terminals where trucks go, right? They don't have a very good data handling policy. So they don't have like data lakes or large data warehouses. What they do is they keep data in spreadsheets. So now we are dealing with spreadsheets, just like we dealt with these large organizations like UNO, like World Food Program, and so on. Here again, in terminals, they have data in spreadsheets rather than large data warehouses. So now again, they're dealing with not very large amounts of data. So in this case, we used weather, traffic, driving style, cargo planning, distance, truck, trailer, whether it had a trailer, all these variables, what we call features, to determine whether we can actually predict the arrival time of trucks to one of these distribution centers. So this looks rather large and complex. When we tried different combinations of these variables, right? So we used, okay, maybe some features are more important than the other features to predict the arrival time of trucks. So we see combinations of this, and then we try combinations of our dependent variable by binning it, by saying that, okay, we are only interested in a 3-hour window. So if the truck can either be late on time or too early, like, sorry, too early on time or very late. So we bin it into 3 classes, and then we do that. So many combinations like this, but we still see that the prediction accuracy with different algorithms that we tried, which is on the columns, is not very much, right? So even if we take 3 kind of classes, we're not doing very well here, right? So they're not super accurate, these algorithms. And then we try to figure out, okay, why this could be happening. Of course, the data is noisy, so we have to take that into account. But there could be other things. So when we try to understand the domain about why these trucks were actually, there were so many trucks that were actually late. And I don't, here we see the distribution of the trucks. Very few trucks are really on time. They're either early or they are late in this kind of distribution, right? So, so when we actually tried to figure out, okay, we asked them why they were coming late, and some of them said that there was no actual incentive to come on time, because if they are too early, actually, if they are too late, they get very nice treatment. So they get a nice warm cup of coffee, and then they can chit chat with their other fellow truckers. It's easier for them to actually do this rather than being exactly on time, and then they are rushed through the terminal. So understanding the domain gives us more insight into why these predictive algorithms don't really work, especially when the data is so small. So what I mean by domain understanding is this concept, like these human concepts, like the truckers were not really incentivized to come on time. And based on that, what Short did was he came up with this rather, let's say, a complex data mining method, which basically boils down to this: how much domain knowledge can you get while making the predictive algorithm? So more domain knowledge you can get, and more theories you can create. So that is stage 2 here. Based on stage 1, the better would your predictive model eventually become. Okay, so that is basically, again, a very high-level view of this research, just to keep time into account. And the good thing about this research was, okay, he also applied it to cases where we don't use this method and the cases where we use this method. So this is again in a terminal, we are trying to see the turnaround time of trucks. And when we apply this method and when we don't apply this method, we see a clear difference. So that is what this slide is about. I won't go into the details here. But if you apply this long drawn method and get all the domain knowledge that you need, our predictive model performs better. Again, stating that idea that when you're dealing with small amounts of data, the domain knowledge is very critical and very important. So, so that's what these slides are about. And these are the results. And you see that S6 is where the domain knowledge is really used. And here with S6, we get better results than the others. So we took this whole concept about learning, so learning from the domain. So when is the domain knowledge really important? So that's the core idea now. And do we use it in the data selection process? So this, firstly, I have to explain that this flow that you see here is the typical, what is called a KDD, knowledge discovery from databases, right? So this is like the first process model that people came up with, or actually that researchers came up with to deal with machine learning or any kind of data analysis. So the question is, at which point is the domain information more important? In data selection, data pre-processing, data transformation, or actually the data mining, right? So what we are thinking right now is, what about the validation, right? So do we also use domain knowledge there in the validation? So what we're thinking now is so this point about where this domain knowledge really required is also kind of related with, can we actually learn with an existing predictive model that has been developed? So someone has made a predictive model for that particular domain. So let's say someone has made a predictive model for arrival time of trucks in this distribution center, and we are trying to figure out whether we can create another predictive model for arrival time of trucks at a completely different distribution center, right? Which is different country, maybe different kind of truckers, different kinds of trucks, different traffic conditions, different weather, whatever. So that would be the same domain, truck arrival in a different setting, different case setting, right? So now the question is, can we actually learn? So that way, if you have very noisy data in another domain, in the same domain, but in another case, in a different country or whatever, having learned the important variables that are required from this particular one predictive model that we created, we can use that same knowledge in this new predictive model, right? So that is the whole idea here in what we call as cross-domain analysis, and where we learn from one predictive model and apply it to another. So this again is done with, under collaboration with the PhD student, which his name is Mayur Ghosh, myself, and the co-supervisor Joaquin Gromifo. And here we see that we can learn, right? So we figured out that that this is possible, that we can learn from one predictive model and apply it to another. And we have done that with trucks arriving at 2 different distribution centers in Netherlands, where for one truck, we used traffic and weather data, and for the other, the traffic and weather data were not so good. But could we learn that this particular traffic data is more influential to the predictive model than this weather data, and so on, right? So even if we have noisy data, can we learn from a predictive model in one domain and apply it to another? That's what we call as cross-domain learning. And I think Floris would also explain something similar in robotics later on, but that's the idea. And so this is our overall model that we have thought about. So one is just to explain how different are the 2 domains against compared to each other. We have something called domain complexity analysis, where we come up with like a metric. How can we differentiate these 2 domains that we are trying to compare with, right? And then the modeling process itself has a predictive score for each domain with different, probably similar factors, because trucks, you'll always try to predict trucks based on weather, road conditions, traffic, type of truck, size of wheel, I don't know, type of driver, driving way, these kinds of things, right? So those factors will never change. What will change is the country it's driving, the traffic conditions of the country, the weather in that country, and so on. And that maybe the driver behavior in that particular country or state or location or whatever. So, so that's why we can actually leverage the insights gained from one, creating a predictive model in one domain and apply it to another. So that is what we have done, and we did it to what's called road feeder service in Europe and distribution centers in Netherlands. And this is just making it more clear, the same model. And we saw that we can figure out the differences more clearly, but also we can determine which are the important features by actually comparing the results of these analysis. And we have just used a simple ANOVA to compare the results of these predictive models. So we won't go into the details here, just to let you know that this is possible. I think I'm running out of time, so I'll go to the key insights, perhaps from this really long presentation, which was meant for 15 minutes, but overshot the time, and apologies for that. The one key insight I hope was clear was that domain understanding is very important for the particular case we are creating the predictive model for. The type of machine learning algorithm is important. So not just for analysis. So there's lots of papers and already lots of discussion that, okay, where is which kind of predictive model is important or useful. So some people say, oh, light GPM is great. And then you have like random forest is also good, like a nice baseline. So you have many predictive models. The question is, have you actually seen the data that you're dealing with? So if it's small data, naturally, you can't use very sophisticated deep learning algorithms. You need to use more traditional algorithms. And then you need, but before you apply that, you need to be aware that maybe when you're dealing with small data, your ground truth itself could be noisy. So that's an important consideration, right? So you have to check the truthfulness of the ground truth. Is it really reliable itself, right? And then maybe apply different techniques to actually check that. And one of that could be unsupervised learning, as I showed you in the World Food Program case. And then maybe these techniques help. So one is complexity-aware data analysis, where we do very sophisticated analysis of trying to understand what the domain is talking about. And we do this by interviewing people, interviewing truckers, or in the case of arrival time of trucks, or interviewing the distribution center people working there. And the other one could be this comparing predictive models across domains. So maybe that's also useful. We can gain insights from one predictive model and apply those insights to another. So that was about it. I know I overshot the time, so apologies for that again. And if you want more information about anything that I presented, you could always send me an email. So that was about it. And I will stop sharing my screen now.
Oh, thank you. I think your passion for data and is so obvious. And what you have done is also not just the dated or information that is, or models that are available or data that is available, but you have also shared more or less state of the art, because some of them are in the pipeline for getting publishing. So thank you for sharing this. I think many have benefited from your overview. Thank you. So you are pardoned for overshooting because you have kept their attention very riveted. Thank you. May I request Dr. Flores to share his thoughts on this subject or his research?
Yes. Can you see my screen?
Yep.
Okay, so thank you so much for inviting me to talk at this seminar. I will be talking mostly about robotics. So to start off, let's think a bit about what makes a robot intelligent. In the past century, we've had great success with industrial robots. And if I ask an industrial robot, can you make me a sandwich? Well, if I pre-programmed it, the industrial robot can make maybe 1,000 sandwiches per hour. But an intelligent robot in my home will face a lot of different issues. So first of all, the robot might ask itself, what is a sandwich? And what kind of sandwich does the user want me to make? What goes into a sandwich? And how can we compose the ingredients of the sandwich? And also, where should I make the sandwich? And when should it be ready? So many of these questions require the user to have a dialogue with the robot. The robot needs to understand words. It needs to understand where things are located and which ingredients we have in the house, how to navigate through the house, how to manipulate objects with high precision, how to reason about tasks, and how to handle dangerous objects such as knives. And actually, we don't want to pre-program the robot to do this because there are so many different tasks we want the robot to do. We cannot pre-program all the tasks. So I think this is the challenge of the 21st century, how to make intelligent robots which can handle kind of simple tasks like this in a way that is acceptable. So I quickly want to introduce our research center here at AST. We're doing research into industrial cyber-physical systems. And we're actually focused mostly on the societal issue of aging. So this is a very leading issue for Japan. Yeah, our working population is expected to decline from 87 million to 60 million. So that's a massive decline in working population. And this will lead to labor shortages and a lot of difficulties in passing on technology and know-how. And our center is focused on improving the situation. And the way we do this is by increasing the productivity per person and also increasing the number of production workers and also efficiently transferring know-how from person to person. And what we do in our center is that we have different test beds to validate the adoption of technologies. So we focus on factories, logistics, drug discovery. These are industries which are labor intensive. So there can be a big benefit of introducing robotics. And I'm personally in the automation research team, which is mostly focused on the retail store and factory scenarios. So let's get deeper into some details. I will present some work which I presented earlier this year at the ICRA conference. This is one of the top conferences in robotics. And this work is on learning how to complete the depth of transparent objects using augmented unpaired data. So for robots, it's very useful to have a depth map of the environment because it will allow the robot to estimate how far it is away from objects and also how to grasp objects. However, when we have transparent objects, we face various difficulties. A transparent depth map might contain missing depth pixels. It might report the background depth instead of the foreground depth. And it might report noisy depth pixels for transparent objects. So in this image, the left and middle picture is what the robot might see. But the rightmost picture is actually how we want the depth map to look like. So in our research, we explore how to create a data set of augmented objects that do not exhibit problematic characteristics. We do this by applying stone spray to glasses. So this solves at least the depth detection problem. But of course, in the real world, we cannot apply stone spray to all our glasses. So instead, we want to collect data sets from the real environment. And actually, we'll collect two data sets. One is a data set of the original transparent objects. One is a data set of the opaque objects. So that's the objects which we spray painted. And also we will collect some small test and validation data sets, which will actually have paired data. But the training has to be done on unpaired training data sets. So in this research, we try to find a network design and training process that can learn to complete depth of transparent objects using only unpaired data. So here I show our collection method. Yeah, we just roughly place the object in a dishwasher and we collect that data with a depth sensor. With this method, we can collect around 500 samples per minute. And this way we collected 30,000 different samples. So for each domain, we have 30,000 samples, which means 60 different scenes, which we recorded data of. And also we collect a small validation data set and test data set, which we collect by manually aligning the objects. So first we place the opaque object, and then we align it with the transparent object. So to get the accurate alignment, it might take a minute for generating one single sample. So now we have an unpaired training data set, but we also need a method of training using this unpaired data set. And for this, we are using a technique called CycleGAN, so cyclic generative adversarial networks. In CycleGAN, we have one generator which transforms elements from domain X to elements that could statistically have been drawn from domain Y. And also we introduce an inverse generator, and we can use this inverse generator to enforce structural consistency. And we also have discriminators which learn how to separate generated elements from sampled elements. So by requiring the generated elements to be revertible to their input data, we encourage the generators not to forget the details from the input data, and also not to hallucinate new details. I saw someone raise his hand, but will we do questions afterwards, or?
Yeah, you carry on.
Okay.
We will put it in the chat box. So,
okay, thank you. So we apply this technique to two different modalities. The first modality is depth to depth, where we have a depth map as input and we want to generate a new depth map. And RGBD to RGBD, where we have a depth map and a color image as inputs and want to convert this to a new completed depth map and a color image. And by applying our technique, we could get these results. So in the first two columns, we show the input color and input depth. And in the third column, we show the result of using our method. And these are the best three samples. We could get, in ideal cases, an error of around 2.5 centimeters. On the fourth column, we can find a state-of-the-art method called ClearGrasp. And the fifth method is a statistical method. And then the final column is the ground truth depth. So if you compare our results with the ground truth depth, you can see that in many cases, our method produces an accurate depth map. We can also analyze this quantitatively by using the validation and test sets which we recorded. In this case, you can see that our method has an error of around 4 centimeters on average, which improves upon the state-of-the-art method ClearGrasp, which has a 5.7 centimeter error. And also it's better than the statistical technique. And this is a video of applying our methods. First, we select which object we want to grasp first. We segment this object out from the scene, and then we use our method to estimate the depth of the object. And then we use this depth to generate a grasp. So using this method, we can unload the whole dishwasher with much higher accuracy than other methods. So I want to talk a bit about how to combine vision and language in the age of foundation models. So foundation models are new models that are trained on large, well, very large training data sets and promise to generalize to scenes which they were not originally trained on. And maybe the first of these methods is called CLIP, which stands for contrastive language and image processing. So with CLIP, we train a text encoder, which encodes a text string. and we train an image encoder, which we give images or image patches. And we want the encodings of the images and the text to be close together in space if they're actually matching. And for cases where the text and the image do not match, we want them to be, or the encodings to be far away in space. So the great thing about this is that now we can query an image using text strings. We can check if the image is actually matching with the text string. We can generate a text string for an image. And also we can combine this kind of technique with like diffusion models to generate new images based on our text strings. So CLIP works on whole images, but in our case, we're often interested in identifying parts of an image. So one way you can do this is by creating a patch-based vision language embedding. So the way we construct this is by generating a feature pyramid of an image and convolving this feature pyramid throughout the image. So that for each pixel in the image, we get a language embedding. So yeah, you can see some examples of patches at different sizes. Yeah, the reason why we take different sizes of patches is because depending on the size of the patch, we might see an entirely different scene. So the first patch might only show us the top of the bottle, whereas the third patch shows us like a much larger scene with multiple objects in it. So depending on which part of the image we are generating embeddings for, we might need a bigger or smaller patch size. So we're creating this pyramid. We make sure that we cover all the different sizes, or at least a variety of sizes of the image. We can use this technique for creating language embeddings for the whole scene, and then we can query the scene using the language embeddings. For example, we can look for where in the image is the drill located, and we generate these kind of heat maps showing where the image features most closely match the text features. And you can see that this quite clearly shows where's the drill located. It also works for objects like soft scrub, which is this this washing detergent, or finding the mustard in the image, finding the potato chips, or even finding like Pringles. So we can switch between using either brand names or category names. For some objects, it might not work so well with the brand name. For example, French's doesn't accurately find the French's mustard. I think this is because yeah, the words might be very confusing. Of course, France is a country, so the network can get confused by this kind of term. So this allows us to create image embeddings for 2D space, but what we want to go to 3D space. To do this, we are exploring a technique called neural radiance fields. And neural radiance fields basically interpolate between different image viewpoints. So within our convenience store, we recorded a video of one of the shelves filled with products. And then we sample different images from this video. And we can interpolate between these images to create what seems like a 3D model of the shelf. However, it should be noted that none of these objects are actually 3D models. So this is a very easy technique or cheap technique to generate a data set of a 3D scene without having to manually model all the objects in the scene. Now we can combine a nerve representation of a scene with CLIP embeddings, creating something called language embedded radiance fields. This was a paper published this year at ICCV. And now we can query the scene using text strings like utensils to find the utensils in the scene, or wooden spoon to find a specific utensil. We can even use abstract queries like where can I find electricity? We can read text strings in the scene, and we can find very specific objects like the blue dish soap or the Waldo figure. or the paper towel roll. And you can even query the scene for visual properties like, okay, what in the scene is yellow? We apply this also to our convenience store. So we can query for example, cup noodle, and it would show us where in the scene we can find all the cup noodles. Or where can we find the Pringles? Or where can we find the macadamia? We can also combine a model like Clip with segment anything to first segment the image into different image patches and then find the objects in the scene. And in contrast with our previous methods where we convolute the entire scene, in this case, we can find specific objects in the scene. For example, finding out where is most likely the drill located, finding the Frenches. Actually, in this case, it works better than the convolution case. Finding where's the mustard, where are the potato chips, where are the Pringles, and where's the soft scrub. So yeah, by combining these foundation models, we can get very good results. And I think one important thing I should mention about the foundation models is that we don't train them at all at our site. We just take a pre-trained network and we can combine different pre-trained networks to get useful results, like, for example, in this case, to locate objects in a scene. So what does the future hold? Well, new technologies like ChatGPT allow us to control robots through voice and dialogue. And also new foundation models allow robots to perceive the world and understand the relationship between the vision and language. And also models like GPT allow robots to reason about complex tasks. And I think these kind of new developments will really help us to realize our dream of having robots that autonomously learn, adapt to their environment, evolve in intelligence, and act alongside human beings, which is the goal of our Moonshot research project. We want to be able to have intelligent robots walk with us by 2050. So I would like to thank my colleagues at AIST. And yeah, let's start some interesting discussion.
Thank you. I think the two perspectives have been very interestingly sort of contrasted, if I may say, because one was focusing on learning, machine learning, and the other was saying, even without my teaching, it can do some tasks which are, I mean, through a process of learning, of course, but, and the success stories that you have presented in a very simplistic way has given us, I think, the audience a view of what the future is in store for us, making everyday life much simpler. I think especially you were saying about Japanese society being aging, and I think you can sit or lie down and order the Pringles to come. I don't know if the Pringles is a right example. Guy who can't walk. But yes, I think noodles may be better. Yeah, okay.
Yeah.
Thank you. I think that's a thanks for sharing the overview of both aspects. So if I may address the sort of first question to Professor Chintan, you did mention about how your key insights about managing data. So I will put it, my first question is primarily to elicit from you, what are the primary challenges faced in managing data for impactful, say, AI models? And what type of strategies, or one or two strategies you did mention about, what did you say? I think it is complexity awareness is what you said. So what are the strategies to overcome these challenges? So my two-part question is, what are the primary challenges in managing data to create a impactful AI? And what are the strategies to overcome these?
Thank you. That's a very interesting question and maybe very useful for practitioners. So I think the main challenge is to understand the key insights from the domain. So what many companies generally do, and many institutions need to do, is gather all relevant, important data that they need and manage it in a very sustainable way. So typically that could mean that they have multiple databases and they could store it in one large data warehouse, which they could use for analysis. Or nowadays they could use data lakes, I think. But this needs to be done continuously and in such a way that it's not an excess of a burden to the company when they want to analyze their data. The question here that comes up is, are these set of features that, or are these data sufficient for the target that they have, right? So if they want to predict maybe the profit or the turnover, are these data that they have actually gathered, is this sufficient to actually make a good predictive model? Or did they lose out by not collecting some other data that was lying around? So that is always going to be a challenge. So that is what we try to do with this cross-domain analysis, actually with both things. Like one is the complex-aware data analytic method. So suppose you approach this as someone who's not working in that company or that institute or dealing with that particular domain, then you're coming in as an outsider and you really need to understand what the experts themselves know. I think that's the essential first step in understanding the domain. So this domain understanding of any complex domain. Now, if you have a very simple domain, for example, a vacuum chamber where you want to know, okay, what happens when you increase the temperature? Yeah, the pressure would increase or the volume will increase, right? So of the gas. So that is a very closed environment, which is, I would say, low in complexity, but many physicists might disagree. They would say this is also has high complexity. But any domain which is in the real world has a high complexity in general. That's why many of these economic models don't really work the way they're supposed to work, because they are dealing with a complex domain. And in some cases, even medicines don't work on a human body because, again, it's a complex domain. So there are too many variables here, and understanding what are the critical, important variables takes a lot of time and a lot of effort. So that is where this complex-aware data analytic method might help, is getting those insights from the relevant experts, because it's almost impossible to gather that as an outsider without having much of an exposure to the domain. And then the next step is, can we actually learn from an existing? So someone might have tried this in the past on that same domain. So they might have built a predictive model on that. Can we actually gain insights from that particular predictive model and apply it to our particular problem question, right? In question. So that will be what I explained as what we call the cross-domain analysis, where we try to learn from one particular instance of a predictive model that has been created, or many instances maybe. Can we actually learn which features were used and how important those features were, so that we look for something similar in this domain? And if it's not available, we can say, we can at least try to figure out why our predictive model is doing badly. Maybe it is because those features are not present, or maybe because those particular features that are so important are so noisy in this particular instance. So I'm not sure if that answered both parts of your question, but
got it.
yeah.
Just as a follow-up on what you just now said, you did give one or two examples earlier about this cross-domain learning applications and the power of that. Can you give another, maybe for a deeper understanding of the subject of cross-domain. From your vast experience in this field, can you give one or two examples of how this has helped the outcomes to become better, cross-domain learning?
Yeah, so that's so what we are currently doing is, okay, this is again work in progress. So this whole cross-domain idea comes from the number of extensively made machine learning models that already exist, right? So the idea is to leverage that when you're trying to create a new model. So what we're currently doing is we are applying it in the area of supply chain, again, in the arrival time of trucks, which seems quite important for many of these distribution centers when they're dealing with, logistics supply chain. They want to know when the trucks would come so that when the ships would come so that the trucks would be ready so that the cargo is loaded and unloaded quickly and most efficiently. So right now we are just looking at it in this particular, let's say, case or domain of arrival time of trucks. But we could potentially even use it, for example, in robotics, like what Floris is doing in his research, and compare any area where there are, of course, data challenges, and it's a complex domain where, okay, we have people managing trucks, people managing ships who are sailing, and also people managing in the whole process in the distribution center. So whenever there are these humans actually involved in that whole process, then you bring in a certain level of complexity because things are never as straightforward as when maybe simulation or when you have robots interacting with each other, which can be kind of pre-programmed, though you can indeed bring in some complexity there. But the human complexity is a different level of complexity. So, whenever we see a predictive model in a complex domain, there's a chance that you can actually learn from that, maybe those critical insights. And in our case, one of the insights we got from the predictive model for arrival time of trucks was that some of these drivers were not even incentivized to come on time. So sometimes if they arrive late or even early, they get more better treatment in the distribution center than when they actually arrive on time. So this is a kind of a thing that you actually understand when you talk to these drivers or talk to the people in the distribution center to understand what's happening in the domain. And these insights could perhaps be used, like we also try to use now, in a new model where maybe some aspects of the domain are missing. So for example, maybe we don't have, in the new model, we don't have any information of the traffic at this particular granularity. So in the first model, we had traffic at maybe the hourly level, and the second model we have only at the daily level. Now the very fact that one of the features is so different brings in some element of noise into our model. So we need to take that into account. Now, if it's possible to get the traffic data at an hourly level, and it just takes a little more effort to do that, probably this cross-domain analysis would tell us maybe that's the way to go to improve your model. So hourly level data would make much of a difference because we have already seen that in this predictive model. The same way, if you don't have weather data at daily level, you have weather data only at maybe a weekly level. Maybe daily level weather data makes a big difference, because if it's raining heavily, the trucks would be delayed more on that particular day than if it rained heavily over the period of the week, like the centimeters of water or whatever. So, so this kind of understanding that we can gain from understanding or analyzing one particular case can be leveraged when we are trying to create a predictive model for the same domain, which will be arrival time of trucks, but in a different setting. So typically you could use that in many different cases, right? So for creating a predictive model, which in any complex domain where it's not very clear what is that effect of that particular feature in this in creating that predictive model. So that is where I think this cross-domain analysis is most effective.
Powerful. Okay, I got it. Just one question. You did mention, Flores, about the employing in a very broad way generative adversarial networks. Can you throw a little more light how this can help generate relevant data for the AI models in your area, which is robotics? And what are the potential applications which will benefit society in general?
Right. So yeah, as I showed you one application of using CycleGAN. CycleGAN is kind of a specific way of applying GAN. Usually when you have a GAN, you would have some supervised data. And one way you can use it, for example, is to make a simulation look more realistic. For example, I might make a simulation of a task, which looks very basic, like very low quality computer graphics. But I also record like real scene data of a task. And then I use a GAN to learn how to transfer from one domain to the other domain. So from the simulated domain to the photorealistic domain. But this is a great way to create data sets for computer vision. And that's one thing which I've seen it being applied mostly. And yeah, I think like this kind of GAN technique, it's used mostly in computer vision domain. So to generate new vision samples. Yeah, there's some studies which apply it like to other like lower dimensional data sets. But yeah, it's really mostly used in the computer vision domain. And also you can use a GAN not just to generate like data for existing data. You can also use GANs to generate whole new data. So in the example I showed you, we take as input RGB data of the transparent objects, and we generate the RGB data for the opaque objects. You can replace the input actually with a random input vector. So we just generate random input, and we use the GAN to generate output. And actually, this is the traditional way in which GANs were used, and it allows to generate basically novel data just by training it on existing data. And then various researchers have tried to find out if I have a GAN trained on random data, can I somehow make the data process or data generation process controllable? So for example, they introduce sliders to control aspects of the scene. Like for example, you can generate new images of cars, and you have a slider which allows to change the color of the car, or a slider which changes the size of the car. Maybe you can configure the amount of windows the car has, the number of wheels, for example. So yeah, this technique has been used a lot in artistic applications, but we're also applying it in more like task-specific applications, like robotics.
Great, great. I think that has given us some idea about this relatively complex subject. Thank you. Just Professor Chintan, you did mention about the deep learning aspects. And can you throw a little more light about the role of what I think is called deep neural networks in handling large data sets? And how do these networks help extract meaningful insights? Because you did mention that it can become very simplistic or too broad. So how do you get insights and patterns from this large data sets? And what are the implications of this in creating models using these large data sets? Because ChatGPT is one such example, but can you throw a little more light on that? You are on mute.
We have applied deep neural nets on a couple of projects. And what we have, so one of the main challenges, like you mentioned, is making it more understandable. And that is always going to be, so this whole thing about explainability is, I think almost a field, or it is a field. Explainable AI, is a field nowadays, and it is a challenge. Making predictive models, especially with deep neural nets, which basically involves multiple layers of neural nets. Some of it is also engineered. So that's one thing that even I didn't know until we start, reading the book on how these neural networks really work, or how deep learning really works. For some tweaks of the neural net, it's not obvious why it should be there. Why that particular layer needs to be in this form, or why the next one should be in this. It's a little bit engineered. So what people have seen over a period of time is this layer following this one, the way it's connected and the way you got to do it, it works the best for this kind of data. Okay, so it's kind of something that these insights have been gained over a period of time, and that's how these architectures have developed. And it's not like suppose you have this particular data set. Oh, this is the right architecture for it. That's not very evident currently, right? So it's a little bit of cyclical doing, and then figuring out, okay, maybe I can tweak it better this way. I mean, that's all for all machine learning, but also especially true in deep neural nets. It's not a given that a particular architecture would work best with some kind of data. Having said that, I think this whole thing about explainability, maybe even Floris can join in. There are certain techniques in which we can try to figure out how this model is actually working. I think these techniques might be even easier with large language models than with trying to figure out other kind of structured data. But some of these techniques are there, which try to say, okay, this is the result you got from this model. Can we actually approximate that particular result by using a more understandable model, like a linear model or something like that? And on that, when we do that, we can actually figure out, okay, which features have what kind of effect on that particular variable. So suppose we take kind of approximate it with more like linear models. Does that make it more clear? That is one kind of approach. The other approach or other family of approaches towards making models more understandable is using kind of a game theoretic understanding. I think these are called Shapley values, where they see, okay, these are the features, and this is the effect that particular feature would have on the final model. And then we can actually compare the effect of different features while removing the feature or adding that feature. And this total effect can be actually visualized very nicely. And we can actually see, okay, which features had how much effect on your target variable. Of course, there could be other techniques also. One of the ways in which in our department we are trying to make more explainable models is by not approximating it with linear models, but more with decision trees. So they are busy with trying to make very, let's say, little more complex decision trees, where at the same time, the idea, the reasoning is that decision trees are easy to understand because they are like this whole bunch of if then else statements. So if this or not this, and you go to this branch or this branch, and that makes understandability of models better. So that is also an approach. So I'm just giving you a very high level ideas about how understandability can be improved. I think I answered your question, but I'm not sure.
Professor Chintan, and to both of you. Maybe this is the last question or last but one. But what we are wanting to understand, because you did say that we really do not know whether a particular, in that model, a particular step is good or not good, but it is giving you a certain result. So does that mean that the optimization models, is it that this is not really an optimum model, but it could be a suboptimal one? Or how does one really work out that this particular model is best for that particular data set?
So,
Doris, would you take that? Okay.
yeah, actually, the large challenge, I think, in machine learning is that we have a data set which you train on. And this data set actually is just a representation of the real data we want to apply the model on. So I think we can build networks which are completely optimized for our training data. The only problem is we don't want them to be optimized for the training data. We want them to be optimized for the whole data set, right? The whole world's data set. So any kind of data we might feed to them, we want to get a good result. So actually, during training, we are not looking for the optimal model for the training data. We're trying to find a model which works well on the training data, but also generalizes well to unseen data. And actually, yeah, by definition, this model will not be the fully optimized model for the training data.
Right. Okay.
Do you understand?
I got a gist of it. Professor Chintan?
Yeah, I think, please just call me Chintan. I think the important thing here is that if you take every part of your training data and use it, so there's a risk of being of your model being overtrained, in the sense that it knows every aspect of the training set, and it might not perform very well with your testing set. So there's a whole thing in machine learning about bias and variance. So how biased is your model, and how much variance it has. So and that's kind of related to the concept of overtraining your model, or let's say even undertraining your model. So if it's overtrained, it's kind of more biased. So it really says, okay, I know everything about this, and that is related to bias. By the way, it's not entirely that. And okay, that this is how it should be. It should work, and that's why we can't be really sure, because we use a part of your data for the training, and then a part for testing, and maybe a part for validation, especially in deep neural nets. One can't be really sure that, okay, this is the exact optimum model that we have. What we can say is, compared to this baseline model, we are performing better. So it's always these small improvements that people make, and that's why it's very important to establish a good baseline. And sometimes they use very simplistic, understandable models for the baseline. And in fact, talking about understandable models, many companies, they don't really like very complex deep neural nets, because not just about making that net deep neural net, but also in maintaining it, and even runtime. It is quite heavy on server space and so on. So so what they prefer is a model that is more understandable, and maybe with fewer layers, which they can handle in a better way. So that's what many organizations go for. So sometimes a simplistic model or very simple model can be better in a given setting than a more complex model. I think this is like a general, let's say, rule of thumb.
Just one last question, if I may, because we are slightly out of time, but how does one actually know? Is there some metric by which you can say this amount of training is adequate, whether it is a robot we are talking about or an app we are talking about? how do you know it is undertrained or overtrained? When do you cut off your training?
Well, one benefit you have is that when you train a model, you can store previous versions of the model. So basically, you can train your model until it starts to overfit the data. So it starts to perform better on the training data than on the validation or test data. And then you just take the previous model which you saved and use that as your final model. So yeah, it's not a huge problem to pick the best performing model. And usually I think you aim to overfit your model at first. And actually, this is a nice hint that actually you can make your model deeper if it starts to overfit.
Yeah.
Wonderful. Thank you, gentlemen, both of you, for joining today's session. And it has given us, I would say, a state of art on all the things that are happening. As we discussed, as you explained as a disclaimer at the beginning, ChatGPT may be a sort of an overkill, but yes, it does play about the large data sets, and ChatGPT does use large data sets, whereas we use in more practical day-to-day, we use small data sets like the truck example or the other examples that you gave. Data sets are limited, but in this limited data sets, noisy data can be addressed, and that is very refreshing to hear. And you guys are working on trying to clean up this and addressing these quick, no, I won't say quick, but addressing them in a systematic manner so that overall society at large will have confidence in these type of systems.
Yeah.
So thank you very much again. And just one point I wanted to bring to your notice, that we at this center, we are working on a working paper series based on these webinars. So for limited, due to the time constraints, we have discussed very limited number of topics on this. But we would like to explore a little more in depth on these working papers. And we request your involvement in producing these working papers, which will again benefit not only the practitioners, not only the academicians, but also the practitioners, both ways. I was about to put it the other way, but first, both of you are academics. So both ways, it should help us to translate. So I hope you will agree to continue to work with this excellence, Center of Excellence at IIM. Thank you.
Thank you for having us.
Thank you for having us. It's been a real honor and a pleasure.
Thank you. Bye-bye.